Welcome back from your break. We're going to be comparing some half cells. Those half cells put together make a galvanic cell. So remember, this is our focus, and we're going to look at She, the standard hydrogen electrode. Before we get into that, let's just talk about the idea of a standard. What do we mean is a standard? Well, in chemistry, we have a whole lot of standards depending on what substances we're looking, what calculations we're doing. So, for example, the standard for a mole, 1 mole is related to 12 grams of carbon isotope 12. And so everything is compared to that. We could also look at the standard volume for gases, and we'd say the standard volume is 22,4 decimeters cubed at a temperature of 273 Kelvin and a pressure of 1 kilopascal, or 101,3 kilopascals at least. So we've got this atmospheric pressure that is a standard unit, and we can use this all the time. We recognize absolute zero is a standard temperature. It's equal to 0 Kelvin or minus 273 degrees Celsius. So chemistry has a whole lot of standards. And a standard just is a way of comparing things against each other. So for electrochemical cells, we need some standard conditions. And the standard conditions here are slightly different to the standard conditions for gases. We're going to say the standard conditions for the cells is a temperature of 25 degrees Celsius, which is the same as 298 Kelvin. We recognize that the concentration needs to be a standard as well. And we're going to take the solutions in a galvanic cell to be 1 mole per decimeter cubed. That's sometimes indicated as 1 molar. Now, not all galvanic cells have just a solution with an electrode. Some of them are gas electrodes, and the standard hydrogen electrode is one of those. It's using hydrogen gas. Where you have a gas electrode, you have an inert electrode, usually a platinum electrode. In some cases, it can be a carbon electrode, but usually a platinum electrode. The pressure for that gas has to be standardized. So the pressure only for gas electrodes, the pressure is going to be 1 atmosphere, which is equivalent to 101,3 kilopascals. And we make sure that we've got that all very clear as we go and look at our standard conditions over here. There would be a standard condition of 25 degrees Celsius, and the other standard condition is each of these solutions must be 1 molar. Okay, there's no gases here. And if that standard condition were met, then we know that that voltmeter will always read the same. And in this case, it happens to be 1,10 volts. And that's always going to be the same if you've got copper and zinc. So we must be very clear about why it's important so that we can compare things equally. Right, now let's go and look at our famous standard hydrogen electrode. Now, this hydrogen electrode, as you can see, it has hydrogen coming in over here. Notice that I called it kilopascals because I divided by 100, but in fact it's 101,325 pascals, same sort of thing. And it's hydrogen gas that's going in there. It runs down here. There's the platinum electrode, and it's going to get into the liquid. The liquid is either hydrochloric acid of 1 mole per decimeter cubed. I've also seen them being used for nitric acid. So as long as it's just one hydrogen being available, then that is the standard hydrogen electrode. Now, you would connect the standard hydrogen electrode to other cells to make a galvanic cell. And the interesting thing, the reason why we're doing this, is we're wanting to use this standard hydrogen electrode as a reference cell. So we're going to use this one as a reference. We're going to test all the other cells against this one and compare the reading on the voltmeter. And so let's do that. And we'll use our examples that we've been doing earlier. Here's the example of comparing the zinc anode with the standard hydrogen electrode being the cathode. And what you'll notice is that zinc is able to donate its electrons, and the electrons move through the voltmeter to the cathode, and at the cathode there is a reaction where the acid is gaining electrons to produce more hydrogen gas, where over here the reaction is the zinc ions, zinc metal is going into solution to produce more zinc ions. So oxidation here, that's why it's an anode, and reduction happening over here. So what I want you to notice very clearly is that we've got a movement of electrodes and we've got a reading on the voltmeter. When the chemists first did this, they said, let's pretend that the hydrogen electrode will always be the anode. And they'll connect it to the voltmeter, expecting electrons to come from the hydrogen electrode. So when we get a negative reading, it's telling us the opposite half cell is giving us the electrons. So in this case, we're going to say the zinc half cell is the better reducing agent. Where this one, we're finding here, this solution is the oxidizing agent. So that's the reason why we're getting a negative reading there. Now, let's take a little bit of time to put that fancy diagram into cell notation. So we've already said that the zinc electrode is the reducing agent. So we're going to write zinc solid. Now, we're then going to put a line, vertical line, and we're going to say, what are the things that are being formed here? Well, it's zinc 2+ ions. They're in aqueous solution. And if it's a standard cell, you might be asked to show the conditions. So in that case, we're saying it's 1 molar. Then we're going to put in place the salt bridge, the link between the two. We're then going to say, what are the oxidizing, what's the oxidizing agent? And the oxidizing agent here is in fact the hydrogen ions. They're in solution, and they're also a concentration of 1 molar. Then we come to the electrode. Now, the electrode isn't really the thing that we're looking at here, because the electrode isn't the physical electrode. It's actually the species that's related to the ions in solution. So that must be the hydrogen gas. And so we're going to be very clear about that. Hydrogen gas, okay, and we'd recognize that's at a particular pressure, 101,3 kilopascals. And the final thing that we're going to do is put in the platinum electrode, which is the solid. So if you follow that pattern, you'll be able to get the cell notation. Very important, and I almost forgot it, we must say at 25 degrees Celsius. Now, the question should ask you to say at standard conditions, or the cell notation of a standard cell. If they do that, then you must put in the details like I have. If they don't, you don't have to. But please always put in your phase indicators. So always put in that it's aqueous or solid or gas, put those in. Right, let's move on. And what I want to move on to here is to show you that when we connect these together, we find that we've got a reading on the voltmeter of minus 0.76. Now, that reading of minus 0.76 is what we call the E naught of the cell. And so when we've compared hydrogen, we said it was the reference, we're going to make the hydrogen half cell 0. And everything is going to be compared to that. And that's why we're calling it the E naught of the cell. It's the reading on the voltmeter. Now, bear this in mind. We're going to do lots and lots of these readings. And in fact, let's move on and we'll look at the next one, which is the copper cell. There's the copper strip. And now what you recognize is we've got a positive reading on the voltmeter, and the standard hydrogen electrode is now the anode. The electrons are coming from that reaction. So this electrode, we're going to get oxidation taking place, whereas at this one, we've got reduction taking place. And you can see the movement of the copper ions onto the electrode, the electrons moving in this direction, and the reading is a positive reading. So that's slightly different from what we had before. Let's make sure that we can write the cell notation for this. Here, we're going to start with the anode. And you'll see we always start with the anode. We're going to start with the anode here as the platinum electrode. The reducing agent in this case is going to be the hydrogen, and it is the gas. I'm not going to put in the pressure because let's just put it in 103 kilopascals. Then we go to the oxidizing species, which is the hydrogen ions in solution. That's 1 molar. We've got the salt bridge. The oxidizing species is the oxidizing agent is copper ions, 1 molar. And the final thing there is the copper solid electrode. If we look at the E naught of the cell, that's the reading on the voltmeter when we're comparing the copper half cell to the standard hydrogen electrode. And in this case, you'll see it's a positive value. And the reason for that being a positive value is this is the anode. And so the reaction, starting from there, the electrons are going in the voltmeter's been connected properly. The electrons are going in the right direction. That's the reading that we're getting for this cell. Now, what happens if we put not the copper together, but we put the zinc and copper together? What's going to happen here? So no longer have we got the standard electron, but what happens if we put the two together? Well, now we've got a formula here which says take the cathode, and the cathode value will always be the one that is the positive value, or the more positive value. Remember, this one is more positive, the copper is more positive, so we're going to say that value of 0.34 minus the anode value, 0.6, and if you do that on a calculator, you'll get 1.10 volts. That's exactly what we're wanting. So guys, we can use these standard electrode potentials, E naught values, on our table to calculate the predicted voltmeter value. So that's quite an important skill. But you know what? I think that we just need to make sure that we recognize this standard potentials can be used in a number of different ways. And so please make sure that you recognize these, learn to work with them, understand the role of the standard hydrogen electrode, and make sure that you can do the calculations of the E naught of the cell using the data given.